This video is part 3 of Chapter 6, Independent Groups Designs for PSY 222, Research Methods in the Psychological Sciences. We left off last time talking generally about some of the steps in the process of doing analysis when we're comparing groups. We haven't really talked about very specific tests at this point, and we really won't be going into a great deal of detail on that until you are working on homework through your Pallant text. That said, what do we, as we do our data analysis and we look at what the pattern of results show us and what the test results might mean, we need to ask ourselves some more questions about what inferential statistics can and cannot tell us and how we need to interpret those results. We use inferential statistics to make decisions. And I think it's important that you kind of underscore that statement. We use inferential statistics to make decisions. We don't use them to prove things or disprove things. We use them to determine whether we can or cannot support the hypotheses that we've set out to test. So in between groups designs, we want to determine whether or not our manipulation of an independent variable that we're interested in has some kind of reliable effect on a dependent variable that we've measured. So we use inferential statistics to essentially answer that question. There are two methods that we can use to make inferences based on our data. We can use null hypothesis testing, and that's what we typically do in research in psychology. We can also use confidence intervals, and I will be transparent. In my training, the focus was very decidedly on hypothesis testing, null hypothesis testing, and not so much on confidence intervals. In my training, it's in part kind of a culture thing within the culture of the discipline of psychology, and perhaps even more so in the sub-discipline of social psychology. We've just tended to lean in that direction. But there are these two basic methods. In null hypothesis testing, in independent groups designs, we're trying to determine whether or not the mean differences that might be evident between groups, say between your experimental group and your control group, are greater than the differences that would have occurred naturally just by chance, by random chance. So if I've randomly assigned participants to an experimental and a control group, there's going to be some natural error. The means it's an infinitesimally small possibility that the means would be identical between the two groups. So there's error variation that would lead to those differences just normally being present just by random chance. So we want to test whether or not the difference we actually observe, we actually see, is significantly larger than what would have occurred by chance, based on a number of criteria. An outcome that's described as statistically significant is one that has a small likelihood of being of occurring if the null hypothesis, and what null hypothesis means is no effect. So when you define the words null hypothesis for yourself, think no effect, no difference, or if you're talking about correlational research, no relationship. So when we have a statistically significant outcome, in the case of between groups designs, that the means for the two groups you're comparing, for example, are indeed different, that outcome is significant. It's measurable enough that you can say that you're able to reject the null hypothesis with reliability. And I'll make that more clear here in a second. So we want to determine whether this independent variable has an effect on the behavior we're actually interested in, And we can also look at the confidence intervals for that difference. And for the purposes of this class, if you were taking a probability and statistics class or even a mathematically oriented data analysis class, you would be doing a much more in-depth exploration of confidence intervals and some of the math behind null hypothesis testing. We're focused more on the design issues and your practical skills in being able to run tests and draw appropriate conclusions. So we're not going to be focused on the detailed mathematical issues. In some statistics courses, you would be calculating confidence intervals and making statistical decisions based on confidence intervals by hand. We're not focusing on doing that in this class. We're taking a more research methods oriented approach and a more practical approach to using statistical software. So just take that as a caveat. Null hypothesis significance testing, which as I said earlier is a bit more normative for the way we use statistics in psychology. What you're doing is using statistical procedures that are appropriate to the data that you have to determine whether, and in the case of between groups differences designs or between groups designs, we want to know if there's a mean difference between the conditions that's larger than what we would have expected by chance. As I said before, you randomly assign people to groups. Let's say you have a design that's a simple one. You have an experimental group and a control group. Just by random error, there are going to be some differences. Now, if you are manipulating the independent variable and your hypothesis is correct that there will be a difference between your two groups, your experimental and control group, what you want to be able to say, if you have a significant result, is that the pattern that you've observed is enough, and that your experimental design has a strong enough internal validity that you can be confident that the finding you've observed did not occur randomly, that it didn't occur by accident. That also suggests that, when I replicate this, I'm probably going to find the same thing, assuming that I have a robust effect. Now, when we talk about null hypothesis significance testing, what we're trying to determine is if the effect of the independent variable manipulation on the dependent variable, we want to be able to say whether or not it's statistically significant. So there's a level of confidence that we need to establish before we can say that the result we have isn't due to chance. And so we want that chance to be low. We want to set the bar pretty high for ourselves to declare an effect statistically significant. So I want to be able to say, and this is like the standard in our field, we want to be able to say that 95% of the time we can count on our declaration of statistical significance and the finding that we've described as being true, as being real, if you will. So we tend to, as your authors put it, scientists tend to agree that outcomes with probabilities or P's of less than 5 times out of 100, and you're probably familiar with the P equal to or less than 0.05 or P less than 0.05. Those are typically declared as statistically significant. And basically what that means is you seeing this pattern. So let's say that you see the people who watched the violent and stigmatizing TV episode showed significantly greater dangerousness ratings than the participants who saw only violent content. You want to be able to say that that pattern is going to be evident 95% of the time if you ran the test over and over again with new samples. You also want to be able to say the reverse. Only 5% of the time would this pattern have been detected by mistake, just by random accident. So we're setting the bar pretty high for declaring that what we have is a difference that is suggestive of the effect that we're testing. So what are the steps involved in null hypothesis testing? Well, first, you assume that the null is true, meaning in the case of between groups designs, that there are no mean differences between the groups. So you're going to start with the assumption there won't be a difference in means between our groups. Then we use the sample means. We use the group means to make an estimate of the population means. Now again, if you were taking a mathematically oriented probability and statistics class, or even a data analysis class in a math program, you would be spending a great deal of time learning the math behind these estimation procedures. We are not taking that approach here in this course. We're taking a more design-oriented approach. But for the moment, kind of follow along with the steps here. We're going to use the sample means. So I take the mean dangerousness ratings for my experimental and control groups. I'm going to use those means to make a guess, to make an estimate of what the population values might be. The observed mean, meaning the ratings, the scores on the scales that I actually collected from my participants, I'm going to ask the question, are these observed mean differences across the groups greater than what we would have expected if we saw the null hypothesis to be true? So you can kind of imagine if I have the actual means that I observed versus versus means that I would expect if there were no differences between groups. So what statisticians have devised here is a way of saying, okay, if the null were true, what would the means look like? If the null were false, what would the means look like? And then we were making a test in order to determine, based on the values we've actually got, based on the actual data that we have, how statistically significant is the result. So in between groups comparisons, a couple of different tests are very common. They are certainly not the only tests that are available. There are many. If you're looking at comparing two sample means, so if you have an experimental group and a control group, just two groups, the test that we typically use is something called a t-test. If they are independent groups, you'll do an independent samples t-test. If they are dependent groups, you'll do a dependent samples t-test, and so on. So t-tests are what are used to compare means across two groups. If you have three or more groups in your study design, so like in my stigma study that I've been using as an example, I had three groups. I had, the violent and stigmatizing episode of TV, just violent TV, and a control group. Then you use what's called an analysis of variance, which produces a statistic referred to with the capital letter F. An F test is what it's often referred to as, or an ANOVA test. And that tests the differences among three or more means, and it produces for you an overall statement that says, among those groups, is there a difference? It doesn't tell you exactly which groups. You have to do post hoc tests to determine that. They're sometimes called pairwise comparisons. And you'll learn more about that in your Pallant homework as the semester progresses. After you've computed the appropriate statistic, so once you know how many conditions do you have, then you choose the appropriate statistic. Once you've done that, you're going to identify a probability level that is associated with that statistic. Now, SPSS and other statistics packages basically does this math for you. In the bad old days, like when I was learning how to do these things, we didn't have stats packages when I was an undergraduate that could do this for us. We had to calculate these things by hand. It was very laborious, very prone to error because there were so many little calculations that you were making. It was very possible to make a simple mistake. By the time I was in graduate school in the late 1980s, early 1990s, we started to be able to use computer packages to more reliably calculate these statistics. At this point, now that you're in an undergraduate, we can use powerful packages like SPSS to do this background math for us really fairly easily and quickly. So what you're doing in step 4 here is identifying the probability associated with the inferential statistic. The p-value, which is, with the data you actually have, what is the likelihood that the finding that you're looking at, that the difference you're describing is due to chance, and that p-value is going to be presented to you when you use SPSS or another kind of statistical package, or you can look it up in a table. In the back of your textbook, there are null hypothesis testing tables for various statistics. We used to have to look those up. Stats packages now kind of give us that information, but it is helpful for illustrative purposes to kind of look at, how big does a p-value based on my sample size have to be in order to be declared significant, or how big does a test statistic have to be for me to be able to declare it significant. We're then going to compare the observed probability value with a predetermined level that we have to beat in order to declare what we found statistically significant. So typically our alpha level, which is another word that's often used to describe a p-value, our predetermined level is usually p has to be less than, not equal to, less than 0.05. And then we can declare the result statistically significant. If it's greater than or equal to 0.05, then we accept the null, meaning no effect, meaning that the difference is not significant. The difference isn't meaningful. Then we conclude the IV did not produce a reliable effect. If the p-value is less than 0.05 in our actual test, comparing the difference between our observed means, then we can conclude that the IV produced an effect on the DB, and that the degree to which there's possibility that finding was in error, we're only going to tolerate a 5% chance that difference that we detected would have happened by mistake. Now, I found this image, I find it useful just to sort of visually lay out when we're doing a probability hypothesis test. We have a test value and we compare it to the table value. If you have a test value that's greater than the table value, the statistically significant chance null hypothesis is not true. That means there's a significant difference between the values. If your test value is less than or equal to the table value, what this means is you have a statistically significant chance null hypothesis is true, as opposed to not true. And that means that there is not a significant difference between the values. When we're looking at so this is the statistic value. Now we're looking at the p-value or the alpha value. If the p-value that's calculated for your statistic is less than the alpha that you've set, for example, less than 0.05, which is what we usually do, then you have, what it means is you have a statistically significant chance null hypothesis is not true, meaning there's a significant difference between the values that you've detected, that you've observed. If the p-value is greater than or equal to the alpha that you've set, which is your bar, what do you have to beat? then you have a statistically significant chance null hypothesis is true. And what that means in actual words is there's not a significant difference between the observed means. Now, if we were using confidence intervals, and you should understand that, confidence intervals and null hypothesis testing, they're related. We use confidence intervals when we're doing null hypothesis testing. But you could do some ways of testing your hypotheses using confidence intervals more directly. A confidence interval is going to be associated with a probability that your sample represents the true population mean. And again, I'm going to say that if you were taking a mathematically oriented statistics course, you would be doing a lot more discussing and practicing with the more detailed math that's behind all of this. The width of an interval tells us how precise our guess is, our estimate is. You want that interval around your estimate to be narrow. The way that I've always thought of this is, if you have a lot of room for messiness around a particular mean, you have less of an ability to say any given individual, are they representative of your larger population? It's kind of that way. It's kind of analogous when you talk about the width of an interval and how confident you can be that your interval actually contains your population mean. What we would do if we were using a confidence interval approach is we would compute using a formula a confidence interval around a sample mean in each of our experimental conditions. So doing that, we want to show, if we were to confidently say that there was an effect for our independent variable, we would want to show that the intervals are not overlapping. The greater the degree of overlap, the less confidence we have that we have an effect of our independent variable. So if confidence intervals overlap, then we lose certainty that what we've got is an actual difference between means. What you would prefer is to see that your experimental and control groups are very different in terms of the way in which they represent the underlying population. So how I visualize this in my head, I know I don't have a normal brain, if you think of the population of scores on, say, a dangerousness scale, rating the dangerousness of people with mental illness, before my manipulation, my control group should be representative of that overriding population. The groups that are exposed to my manipulation, my independent variable, watching the TV episodes that contain either violence alone or violence plus stigmatizing material, once I intervene, what I want to see is that my finding representing the control group, that should be reflective of the population mean. The other two groups, I should see divergence. And I want to see that the confidence intervals overlap very little before I can say with confidence, and that's why they're called confidence intervals, I want to be able to say with confidence that the differences are reliable and that they represent a true mean difference. If the intervals overlap a lot, now remember that figure that I showed you that showed the difference is in effect size? Use that visual in your head. If the intervals overlap such that the mean of one group lies within the interval of another group, you can say that the means don't really differ very much. So this is it's similar in a lot of ways to that image that I gave you earlier, looking at how to think about effect sizes. Now one way of thinking about this is, what can data analysis tell us? Well, there are a lot of things that it can tell us, but there are a lot of things it can't. And I actually think it's more instructive to remind yourself repeatedly of what data analysis can't do. So if our experiment has good internal validity, the results are significant, and they confirm our hypotheses, can you 100% say that you've proven the independent variable had an effect or didn't have an effect? No, you can't. You will find that if you say something in a research report and I look at it and you say the word prove, I'm going to, electronically scratch it out and say, no, you can't prove anything with findings that you've got. You can either confirm or disconfirm that the pattern of data that you have with a reasonable degree of certainty supports your hypothesis. So the results of your data analysis can't tell us whether the results 100% have the effect that you say they have. They can only tell you with a certain degree of confidence that your hypothesis was supported. You can also, data analysis can't really tell you the practical significance of what you found. For example, with my stigma study, I had to, with the audience when I presented this at a conference, I had to very carefully talk about the practical significance of my findings, because my college student participants tended not to see people, in a general sense, people with mental illness as particularly violent. When they watched violent and stigmatizing TV, their ratings did move in a more dangerousness direction, but they didn't go from seeing people as not violent to ridiculously violent. They went from seeing people as not particularly violent to maybe a little more violent than that. So that has something to say about practical significance. And that's really the art of research interpretation, the interpretation of findings. When we write research manuscripts, that's the whole point of a discussion section, is for you, the researcher, to really think through what might these findings mean in the real world. You have to do that. That's what the researcher's brain does. Statistical tests can only tell you about a very limited number of things. When outcomes are significant, our analysis isn't going to give us absolute 100% certainty. We don't have that kind of omniscient power. And again, that's where the researcher's brain comes in. You have to really think about what are the pitfalls, what are the potential meanings of my finding, given my understanding of theory, given my understanding of the research and the literature, and given my understanding of the limitations of the test that I'm running. When you have an outcome that isn't statistically significant, you can't conclude 100% that the independent variable didn't have an effect. You have to, again, use your big researcher brain to make appropriate interpretations, whether you have a significant or non-significant result. All you can conclude based on your data analysis, if you have a non-significant result, is that there's not sufficient evidence in your experiment to show that the independent variable can produce an effect. Now, if you replicate and replicate and you continue to show that an independent variable is not producing an effect that's consistent with your hypotheses, then you have accumulating evidence that the relationship you predicted is just not holding up. So then you have to go back and rethink your theory and rethink your hypotheses. If you have a statistically significant result and on replication that result holds up, across situations and using somewhat different methodologies, the same findings keep coming up, then you're gaining more and more evidence that the pattern that you're detecting is robust and it supports your theory. That's how science works. We can't prove 100%. It's not like, at the scene of the crime there was a blood sample and you have a DNA test and it proves that that's the killer. We don't do that. in our science. We have to work within probabilities and likelihoods. And that's why you'll find that in your writing, if you use words like proof, we're going to get, we're going to tell you no. You can't do that. You have to be a bit more circumspect than that. Now, to get technical with you, there are certain kinds of errors that we can make when we're making these inferences. So inferential statistics, you're making an inference about the nature of the finding that you've produced. So as researchers, we have to rely on probability judgments. And, essentially is how right am I? How likely is it that I'm right in the judgment that I'm making about the potential effect of my independent variables? Because there's always a chance you're wrong. There's always a chance that error has leaked in. There's always a chance of making a mistake. So when we make a statement that you have a finding that is statistically significant, but the null hypothesis is actually true, that's called a type 1 error. So if we say that there's a finding, that there's a statistically significant finding, but in reality there shouldn't have been, meaning there's no real effect of your IB, that's a type 1 error. If we conclude we have insufficient evidence, when we conclude we don't have the evidence to reject the null, and it's in fact false, so that means we look at the pattern, we run the test, and we claim, there's no effect. But in fact, within the real world of where these variables play, there is an effect, but we haven't detected it. That's a type 2 error. What's important for us as researchers is that we have to think about inferential statistics as a tool. They are just a tool. And any one experiment is prone to a certain level of error. Now, the level of error that we're willing to tolerate, basically, is a 5% chance of screwing up, of making the wrong judgment. And that underscores and underscores and underscores the real importance of doing replication studies, replicating within our own labs, and having replication in other labs by other researchers is really, really important. Since I'm a visual person, here's another way of representing these possible types of errors and the statistical kind of characters that we use to write about them. So you have reality, what's true in the real world, and then you have your findings in your particular study. If you, in reality, you have a test result, and this is sometimes referred to as power. You don't need to worry about that. I'm just using the graphic so that you have a way of, visually kind of representing these different types of things. If you find a significant result, and in reality it's actually true. So if you find a statistically significant difference between groups in your study and in the real world, that's actually the case, then it's a true result. So it's a correct interpretation. That's sometimes called by people a true positive result. Think of it as, just to put it in COVID terms, if you actually have COVID and you get a positive test result, that's a true positive. Now over here, if you find a non-significant test result or you find a statistically significant test result in your study, but in reality there's no difference between groups, that's a false positive. That would be like you take one of those rapid COVID tests and it tests you positive, but in reality you don't have the virus. You take a more robust test and it shows that that was a false positive test. That's a type 1 error. If you found a non-significant difference in your study between your groups, and when in the real world you should have detected a finding, that's a false negative That's a type 2 error. It's referred to with the Greek beta. If you find a non-significant test result in your actual study, when in reality there is no difference between groups, that's a true negative. Now, we eventually need to deal with the issue of external validity. I mentioned in part one that, the major limitation to experimental methods is how do we generalize to the real messy world? And the major advantage to experimental methods is high degrees of internal validity, which you only get because you're strictly controlling every aspect of the experimental situation. Experiments have external validity when you can apply them across individuals, across settings, across conditions that go outside of your original experimental context. So can I take it to other populations? Can I take it to other settings? Can I take my method and vary some of the conditions? That's how you establish external validity. In some programs of research, so in some investigations, researchers may, at least at the start, and this is how it happens a lot, you start, it's kind of like a proof of concept test. You start with the strictest experimental controls, the highest level of internal validity first, so you can test the effect under high degrees of control. And then in successive iterations of your study, you're going to kind of systematically up the external validity and decrease the controls and see if your finding holds. Your authors talk about how, in some investigations you're going to emphasize internal over external, and what you're giving up, you're increasing your ability to make causal conclusions, but what you're giving up is the ability to apply the finding to the real world. Other researchers may emphasize the external. Now, when your authors talk about the necessity for a multi-method approach, this is what they're really getting at, is the fact that some research needs to emphasize internal validity and ramp up the ability to make causal conclusions. Other research, in order to validate that finding, to really put it to the test in the messy, non-controlled real world, that's the true test, is when you combine those findings and you can look at the big picture of the work as a whole, then you have a robust set of findings and you can really talk about the validity of your theory. Field experiments is a nice mixture. I think I've used the example in past lectures of the bystander effect research programs, where the initial studies on bystander effect were done in carefully controlled research laboratory situations, but then the researchers took their bag of tricks and they set up fake emergencies in subways, on buses, in malls, on the street, in rural areas, in urban areas, all over the place. That's, field experimentation, where you're systematically manipulating variables, but you're doing it in a high external validity location. Field experiments are that nice mix between experimental control and real-world naturalism. And so it's an attractive technique for increasing the level of external validity in an experimental design. You can also use, another way to increase your external validity is doing some partial replications in more naturalistic environments. And that can help to support findings that you may have generated in a strictly controlled, high internal validity setting. So we often what we want to do in terms of our goals is to be able to generalize our results that we've tested experimentally. We want to be able to take those findings and look at how they play out under specific conditions. When we can do that, and I keep using this word robust, when we can show that we get this same pattern of findings in multiple contexts, especially if we're able to show that the same findings can be produced by multiple researchers using slightly different methods and manipulations. If we keep finding the same patterns, that's a robust finding. If we don't, then we have to ask some questions about what are the limitations of the finding that we're producing. Now so far, we've really been restricting ourselves to random groups designs. Now we need to spend a little bit of time talking about other alternatives for controlling for the error that's based on individual differences between subjects. Match groups design are one way to do that. If you know you have a subject population that varies on a number of usually demographic dimensions, you may want to be very systematic in making sure that your groups, your independent variable groups, have roughly equivalent levels of those dimensions. So say you know that there's a difference in the level of education of your subject population, or you know that there are different levels or different percentages of your sample are likely to have different racial background or identify different sex, whatever. In match groups designs, you're going to make sure that each of your experimental groups has the same proportion or the same percentage of those various demographic groups. Matching, you could also do matching based on pretest values. So if you have a dependent variable of interest, you want to get a starting point. You want to make sure that after pretest, you're going to randomly assign people, and you're going to check and make sure that you have an equal distribution based on your pretest scores in each of your experimental groups. Once subjects are matched, either based on demographic characteristics or on a matching variable that you pretest, then you do the random assignment. So you might say you have subject A and subject B, and they're matched based on their demographic characteristics. Then you're going to randomly assign them to groups, and that enables you to when you have a matching variable available, it enables you to say that you've spread out the error associated with either that demographic characteristic or the pretest variable. Match group designs are useful when you have when you have access to a good matching variable, or when you have a really small sample. So if you have a small sample size, it's going to be more vulnerable to the error that's associated with some of these individual differences. And therefore, you're going to want to make sure that you match your samples. So for example, if I have a small sample and it's college students, but I know that most of my sample is going to be quote unquote traditional college age students, but there's going to be a small percentage of that population that will be so-called non-traditional, so not between 18 and 22, say people who are returning to school or who are significantly older. And that subset, that older subset, they're going to be even less frequent. So I'm going to want to make sure that I have a matching number of those non-traditionals in my groups so that I am better representing the true population. So for example, sorry, that's a really crappy image. If my independent variable is how much sleep, and I have two groups, I've manipulated the independent variable, group 1 gets to sleep 2 hours, group 2 gets to sleep 10 hours. Whoever gets to sleep 10 hours, that's madness. Group A has 10 students. Group B, I'm going to have 10 more students, but I'm going to match them to the age level, their gender distribution, and their normal level of sleeping length. So here, the first two of these, age and gender, those are demographic variables that you can match your sample on. Normal sleep length time, that would be a pretest measure. And then you're going to measure your dependent variable. By matching the first 10 students who have a known age, a known reported gender, and a known measured normal sleeping length, I can match the pairs. So I have a student who is, say, 22 and female and usually sleeps 7 hours. So I'm going to have one of those people in group A and one in group B, and so on. It may seem unnecessarily tedious, but it's a very powerful technique to use. Now, in addition to random groups and matched groups, we also have naturally occurring groups. Now, when I was being raised as a researcher, we sometimes called these quasi-experimental designs, but I've noticed, and I will apologize if I switch to using that term at some point, your authors use quasi-experimental in a slightly different way. So I'll try really hard to avoid doing that. If you have an individual difference variable, or what's called a subject variable, such as sex or race or class rank, for example, those are natural, quote-unquote, natural groups, meaning the subject comes with that designation. You haven't randomly assigned them to those designations. So you can't manipulate those category designations. They just are. They're just present. So they're called natural groups. Natural groups designs are often described, and your authors do this, they describe them as correlational studies, which I've always found confusing. So if it's confusing to you, you're in company there. It's referred to as quote-unquote correlational because in part you really are limited in your ability to make causal conclusions. So let's say you're looking for sex differences. Go back to that example I used in part 2 of comparing males and females in spatial skills tests. You've got a natural groups designed there. You have a group of males and a group of females, and you want to test, are they different? Now, your authors are going to use the term correlational to describe that research because you're really just looking for covariation between the natural group variable and the dependent measure. So in my example, you're looking at the natural groups variable is the subject's sex, male versus female, for example, and the dependent variable is their score on a spatial skills test. Now, from a stats point of view, you're still going to do an independent samples t-test to compare means between the two groups. You're not running a correlation statistic, but what your authors are trying to suggest there, and this is just sort of the language of research methods in our fields, what's being underscored there is since you didn't do random assignment, you are essentially doing a correlational design. I wish they would be more clear, and back in my day when we were being raised up as researchers, when I was in graduate school, that's why we called these sort of experimental. It's experimental, but not in the sense that you're randomly assigning groups. You're taking advantage of a natural difference between two samples who represent perhaps different populations, and you're comparing them on a dependent variable of interest. When you've got a natural groups design, and the reason they're using this word correlational is so that they really underscore this point in the gray box. Causal inferences can't be made. So let's say you do find a statistically significant difference between males and females in spatial skills test scores. Does that mean that because they're male, males are better at spatial skills? No, it doesn't. There's a whole host of other potential variables that could be driving that effect. And in fact, lots of research has shown that school experiences, the tendency to discourage girls away from certain types of play that encourage spatial skill development, tendencies to discourage girls from moving beyond a certain level of mathematics education, for example. If you control for those things, the differences disappear pretty rapidly. So what they're underscoring for you by calling it correlational is the fact that you cannot make causal inferences based on a natural group's design. As a practical matter, the test that you run, say if you're doing a comparison between a male group and a female group, for example, you're going to run a t-test and you're going to compare groups. You're not going to run a correlation test. So the language here, and the reason I'm belaboring the point, is because this language can confuse you down the road. So I want you to get it clear in your head now. So that concludes part 3 of chapter 6.